Question 1, this is the symbol. That number, bottom left, is the atomic number, and remember that is defined as the number of protons in the nucleus. So we straight away know there are 51 protons. This number, top left, is the mass number. So that one is protons plus neutrons. That one was just the protons. So if we take the protons away from the protons plus neutrons, we get the neutrons. And 123 minus 51 is 72, so that's the number of neutrons. And then this number tells us obviously the charge on the particle, and the point is if it were an atom it would have the same number of protons and electrons, so 51, but if it's 3 plus, that means it's lost 3 electrons. You must get that the right way around. Remember, electrons are negatively charged, so if you've got a positive ion it's because it's lost electrons, and it's lost 3 of them, so 51 to start with, same as the protons, minus 3 gives you 48 electrons, and that means that the answer is C. Question 2 is in effect asking us what happens when you add iodine to chloride. Is there going to be a reaction or not? So what you have to remember is that as you go down group 7, chlorine, bromine, iodine, the ability to attract an extra electron into the outer shell decreases. Because remember, you're adding on more electron shells at a bigger distance from the nucleus, so the attraction to outer electrons decreases. And the consequence is that when you set up competitions like this, the element that's higher in the group attracts the electron more strongly and therefore always ends up as the negative ion. So in this case, chlorine is already the negative ion. It will hang on to its electron more strongly than iodine can attract it, and so there will be no reaction. The colour, therefore, is just dependent on what these are. Remember, the negative ions are always colourless, so there's no contribution from that. But aqueous iodine, and these are aqueous solutions, is brown. Okay, not purple. Purple is the colour that iodine gives in an organic solvent, but aqueous iodine is brown, and therefore the answer is B. Question 3 is a boiling point question. So we first of all have to decide what kind of structures these have. Well, selenium, hydrogen, sulfur and hydrogen, they're all non-metals, so we know these are going to be covalent compounds. And because we've got no evidence to the contrary, we assume that they're going to be simple molecular. Don't go there with giant covalent compounds unless you have good reason to, because they're very unusual. So we're going to say, right, these are simple molecular, and therefore when they boil, we only have to break the intermolecular forces that are holding the liquid together. So the strength of the covalent bonds is irrelevant because those don't break, so we can straight away rule out C. We can also rule out D. The mass of individual molecules is not a relevant issue when it comes to breaking intermolecular forces. So it's between A and B. Is it about induced dipole-dipole forces being stronger in H2SE that causes it to have a higher boiling point, or is it about permanent dipole-dipole forces? So we need to think about the trends down the group. So remember, sulfur is above selenium, and as you go down the group the electronegativity decreases. Okay, because again that's about ability to attract electrons in the outer shell, so it's related to what we were thinking about in the previous question. As you go down the group, the extra shells of electrons mean that the ability to attract an electron in the outer shell, which would include the ability to attract a bonding electron, decreases. So if we think about these molecules, H2S, we're going to expect the sulfur to be more electronegative than hydrogen. Most non-metals are more electronegative than hydrogen, so that's going to be delta minus, this is going to be delta plus. In H2SE, the ability of the selenium to pull those electrons away from the hydrogen is going to be decreased because it's less electronegative, so we're going to have a smaller dipole. Okay, we're just going to have weaker attraction of the electrons towards the selenium. So we expect the molecule to be less polar than in the case of H2S because of the decreased electronegativity of selenium, so that can't be the answer, so that rules out B. So it's pretty much got to be A. Does that make sense? Well, yes, it does, because remember that the strength of induced dipole-dipole forces depends on the number of electrons per molecule, and Selenium, clearly, because it's the next row down, has a lot more electrons than sulfur does, so you would expect this molecule to form stronger induced dipole-dipole forces, therefore to require more energy to break those forces, and therefore to have a higher boiling point. So all of that fits and says yes, the answer is A. Question 4 is about aluminium sulfate. So the first job is to make sure we get the formula of that right. Don't guess, think about the charges on the ions. So aluminium, remember, is in group 3, and so it will form 3 plus ions. Sulfate is one of those that you should have memorized, is SO4 2 minus. Make sure you know those polyatomic ions, the common ones like sulfate, nitrate, carbonate, and so on. So it's not just going to be AlSO4, because those charges don't balance. To make that work out, we're going to need 2 of those to give you 6 plus, 3 of those to give you 6 minus. So it will be Al2SO4 3 is the formula. So then it's asking us about what happens if we have 10 moles of that. Remember, what that formula means is that each mole contains 2 moles of aluminium ions and 3 moles of sulfate ions. Make sure you know what those little numbers mean. Each mole contains 2 moles of aluminium ions, 3 moles of sulfate ions, and therefore in 10 moles we will have 3 lots of 10, means 30 moles of sulfate ions. So then we can convert that into the actual number of ions, remembering the relationship, which is that the number of particles is equal to moles times Avogadro's number. So you've got to make sure you remember that relationship. And Avogadro's number, remember, is on your data sheet. So that's equal to 30 times 6.02 times 10 to the 23, which your calculator will tell you is 1.806 times 10 to the 25 ions. Round that to 3 significant figures and you get 1.81 times 10 to the 25, and so the answer is A. So question 5. Whenever you have a question like this which is about enthalpy changes, delta H, and temperature rises or temperature drops, the key equation is always going to be this one, Q is equal to mc delta T, which you need to know. And that, remember, means that the heat transferred is equal to the mass of the stuff being heated or cooled times the specific heat capacity times the temperature change. Now in this case the question asks us to actually calculate delta T, so the first thing we need to do is rearrange that equation, and that's easily done because, remember, all we've got to do is to get rid of these terms by moving them over to the other side, and that just involves sliding them diagonally like you always do when you rearrange these equations. So it slides diagonally over to there, and so you get Q divided by mc is equal to delta T. And then we've just got to find the numbers to put into there. Now it tells us that delta H is minus 1370 kilojoules per mole of the compound that's reacting, and it tells us that we've got 0.1 moles. So if each mole gives 1370 kilojoules out, we've only got a tenth of that, 0.1, so we only have a tenth as much heat. So that means that we have 137 kilojoules of heat are transferred. So that's Q, but we've got to be careful, because if you look at C on your data sheet, it's in units of joules per Kelvin per gram. And the key thing is that it's joules, not kilojoules, and therefore to be compatible, this has to be in joules as well. So that's equal to 137,000 joules. Okay, so that's our value for Q. So we can put that into there and say that's 137,000 divided by M. Well, M is the mass of the water being heated, and that needs to be in grams, again, to be compatible with that. So 1 kilogram is 1,000 grams, times C comes from your data sheet, is the specific heat capacity of water, because it's water being heated. So that's 4.18. And if you work that number out, it comes to be 32.8 degrees C, or 32.8 Kelvin, but remember the size of a Kelvin is the same as a degree C. So it's 32.8 degrees C is the answer, and therefore it's C. Question 6 is asking us for the number of aldehydes which have that molecular formula. So 5 carbon aldehydes. When you get a question like this, the thing to do is to try to be systematic. So let's start with the simplest one, which would be a chain of 5. So 5 carbons, an aldehyde group is just a carbonyl group at the end of the chain. So that will be the first one. And then we say, right, what if you only have a chain of 4 and you put a branch in it? So we'll have then, that will be the chain of 4, and the question is how many different ways can we put a branch in it? Well, we can put it next to the aldehyde group, that would be 1, or we can put it at the next position along, and that would be 2. And of course if we put it on that one, that would just take us back to there again. So those are the only 2 branched ones with a chain of 4. And then you go to the next possibility, which is what if you just have a chain of 3? So that would be the chain of 3. You've got 2 more carbons, and the only way we can put those on as branches is to have them both at that position. And those are the only possibilities. If we had a chain of 2, there isn't room to put all the other possibilities onto there. So that appears to be the answer, but there's a hugely important prompt in the question which says include structural isomers, which is what we've been doing so far, but also stereoisomers. If it says that in the question, it's likely to be a big clue that there will be stereoisomerism going on. It can't be EZ because there's no alkene groups in there, so it's got to be optical isomerism. So what we've got to do is to go through and look for chiral centres. So nothing there, but this one has a chiral centre, because you can see that carbon has 4 different groups: an ethyl group, a methyl group, a carbonyl group and a hydrogen. So 4 different groups around that one, and that means that there will be 2 of those, 2 optical isomers of that structure. This one has no chiral centres. You might look twice at that one, but it's got 2 methyl groups attached. As soon as you have 2 groups the same, it's not chiral. And likewise this has no chiral centre because you've got 3 groups the same attached to that one. So that's the only chiral centre in all of the isomers. So we've got 1, 2, 3, because there are 2 of those, 4, 5 isomers altogether, and therefore the answer is A. Question 7 is about activation energies for forward and back reactions. I think the easiest way to do questions like this is just to scribble down a quick picture. So we have reactants on, remember this is an enthalpy axis. You only need to do this very roughly because obviously there's no mark for this, but this is going to help you do the working. So you've got reactants there, and it tells you that delta H is minus 51, so it's an exothermic reaction. So these are the products, and this number is minus 51. And then it tells us that the activation energy for the forward reaction is plus 140. So the activation energy is the energy to reach the top of the curve that represents the progress of the reaction. So it's telling us that that is plus 140. And it says what's the activation energy for the reverse reaction? And obviously what that corresponds to is the distance from the product back up to the top of the hill, so it's that. And the reason I've sketched the diagram is that it's kind of very obvious from the diagram that it's 140 plus 51 is plus 191 kilojoules per mole, and therefore the answer is B. If you really don't like diagrams, you can just memorize the formula, which is that delta H is equal to the forward activation energy minus the reverse activation energy. And you can see how that works in the context of the diagram, but if you just want to memorize the formula, you can see that will also give you the right number, because if we rearrange that, we get that the activation energy for the reverse reaction is equal to the forward one minus delta H. So that's 191 minus 140. Sorry, try that one again. It's 140 minus 51. Okay, so it's 140 minus 51 is equal to 191. So that would give you the right answer, but I think unless you really don't like pictures, it's much easier to work it out just from the diagram. Question 8 is about alkene polymerization. So remember that what we've learned is the general sort of recipe for this is that if you have an alkene like that with whatever thing's on the end there. If you have n of those, they polymerize together to give you a long chain in which the repeat unit is that where the 4 things on the end of those bonds correspond to the 4 things here. So in our case, we're being asked about polybute-1-ene. So if this is bute-1-ene, that means that the first carbon is at the end of the chain, so that's carbon 1, 2, and then we'll have CH2, CH3 there, and a hydrogen there, and that means the repeat unit is going to have those 4 things on the ends like this. And the thing is, in this question, that repeat unit was drawn out as a skeletal formula, and in a slightly odd way, but you just have to work out which one of those 4 corresponds to that. So if we draw it out as a skeletal formula, you can see if we've got the bond coming in at the end there through the bracket, we then have one linking bond, which is this one to this one there, and then another one going out through the bracket at that end. So that's the main chain. This carbon, the way I've drawn it there, just has 2 hydrogens attached, so there's nothing to show in the skeletal formula. This one has a hydrogen and an ethyl group, so your ethyl group is going to look like that. And none of them look exactly like that, but you can see that C is just that rotated round through 180 degrees, so it's drawn, if you imagine just rotating that round like that, it's drawn like this, and therefore that's the right answer. So C is the right one there. Just do it in the way you're familiar with. You probably have learnt it like this, that's the way we taught it, but just be confident to say, right, once I've drawn that, I can turn that into a skeletal formula and say which one does it look like, and then that was quite easy. Question 9 then is about this compound, and the first thing we have to do therefore is to get its structure right. So starting with the bute tells us that we have a chain of 4 carbons, and it's bute-3-ene. So if this is carbon 1, carbon 2, carbon 3 is where the double bond starts, so that's going to be 3 to 4. And we know that at carbon 4 we have a phenyl group, and because it's the E isomer, it's going to be on the opposite side from that one, because that carbon chain and the phenyl group are going to be the priority ones, so they'll be on opposite sides. So the phenyl group, which is just a benzene ring, will go there. And then we've got 2-one, which means that carbon 2 is a ketone group, and so we have that, and that's then the whole formula of the compound. Then we have to figure out how many pi electrons does it have. So remember, first of all, a benzene ring has 6. Remember the way it works, each of the carbons of the benzene ring has one of those p orbitals lined up side by side to make the delocalized system, and each of those p orbitals contains 1 electron from each carbon, so we've got a total of 6 around there. So 6 from the delocalized system. And then the alkene group, remember, is a sigma bond plus a pi bond, and each of those is a shared pair of electrons, so the pi bond is just 1 shared pair, and therefore that's 2 pi electrons there. And the same with the carbonyl group, a sigma bond and a pi bond, so 1 pi bond equals 2 electrons, so we've got another 2 there, and therefore the answer is 6 plus 2 plus 2 makes 10, which means that the answer is D. And there we are. In question 10, we have to decide which one of these 4 processes has the lowest activation energy. So this is about remembering what activation energy is the energy that you have to put in to break, or at least partially break, some bonds in order to get a reaction started, so that you can then rearrange the bonds and make new ones. So the more difficult it is to break those bonds, in other words, the higher the bond energy, the higher the activation energy is going to be. So that looks difficult because you think, how am I supposed to know what the bond energies are? But the key thing, just scanning down them, is that, well, this one involves breaking a bond. You've got to break a CH bond. This one involves breaking a bond because you're breaking up the chlorine, so you've got to break a Cl-Cl bond. The last one involves breaking a Br-Br bond because the bromines end up separately. But C is the interesting one, because you can see in C none of these bonds get broken because the CH3 is still intact, The BR is still intact, all they've done is join together. So C is the one that stands out because there is no bond breaking involved. All that happens is that they come together and form a bond. So if you don't have to break a bond, you don't expect there to be much of an activation energy. So the answer is simply C for that reason, because it's the only one that doesn't involve breaking a bond. Question 11 is about this compound reacting with calcium hydroxide. So this compound contains acid groups. Calcium hydroxide is an alkali, so it's just an acid-base question. So what we have to do first of all is identify how many acidic groups we've got in this compound. So 3 OH groups. If we look at the first one on this side, that's a phenol because it's OH directly attached to a benzene ring, and what you know is that phenols are weakly acidic. So they won't react with very weak bases like carbonate, but they do react with hydroxides. So that's our first acid, and so that will produce 1 H+, which can react with 1 OH-. This is a carboxylic acid group, COOH, so again, the name tells you that's acidic. So again, that OH will produce 1 H+. This OH, however, is an alcohol. You've got to make sure you see that. It looks a little bit like a carboxylic acid, but there's a CH2 in the middle there, COCH2OH. That's not a carboxylic acid group. That's an alcohol group, and alcohols are not acidic. So there is no H+ from that one. So that means that 1 mole of this compound will produce 2 moles of H+, one from there and one from there. Now calcium hydroxide, again you've got to be very careful with the formula. Okay, calcium is 2+ because it's in group 2, OH- you know is hydroxide, and so the formula of calcium hydroxide is not just CaOH, it's CaOH2, which means that each mole of calcium hydroxide produces 2 moles of OH-. So we've got 2 moles of H+ from our acid, 2 moles of OH- from calcium hydroxide, and therefore it's going to be a 1-to-1 reaction because the acid-base reaction is just H+ plus OH- goes to H2O. Okay, so 2 moles of H+ per mole of this, 2 moles of OH- per mole of calcium hydroxide, so the moles that react will be equal, and therefore the answer is B. Okay, question 12 is asking us to calculate a pre-exponential factor. So that immediately tells you this is an Arrhenius question. In your datasheet you have 2 forms of the Arrhenius equation. If you're wanting to do a graph of the natural log of k against 1 over t, or interpret such a graph, then you want the logarithmic form. But here it's easier just to use the direct form which comes from your datasheet, which is k is equal to a, that's the number we want, that's the pre-exponential factor, times e to the minus ea over rt. So first job is to rearrange that equation to get a. So as with all these things, it's just a simple matter of rearranging it and thinking, right, I want to move that over to the other side. If you do maths, you might be able to think of an elegant way to do that, but we're not interested in elegance, we just want to get the answer. So we'll just slide it across diagonally like you normally do and say it's k divided by e to the minus ea over rt. And then we've literally just got to put the numbers in. That's all you had to do in this question. So k, it told us, was equal to 0.00315. And then it's e to the minus. Remember, the e to the x function is just a function on your calculator. This is not the time to worry about what that means. You've just got to plug it in. So it's e to the minus. Now the activation energy, it tells us, is 85.0 kilojoules per mole. But we've got to be very careful, because if you look in your datasheet, R, which is the other number here, is equal to 8.314 joules per Kelvin per mole. So it's in joules, and therefore the activation energy also has to be in joules. So that's not just going to be 85, but it's going to be 85,000. R, as we just said, is 8.314. And the temperature is 25 degrees C, but again, the units there of R tell you that the temperature's got to be in Kelvin to be compatible. So 25 degrees C, we add 273 to turn it into Kelvin, and that gives us 298. So that's the sum we've got to do. 0.00315 divided by e to the minus 85,000 divided by 8.314 times 298. So you've obviously got to be careful entering it into your calculator to make sure that you put the brackets in correctly and so on. But if you do that, the answer you should get is 2.50 times 10 to the 12. The units of the pre-exponential factor are the same as the units of the rate constant, so if it's a first order reaction there'll be seconds to the minus 1, but we don't care about those in this question, we just want the value, and that tells us that the right answer is A.